Thank you for the introduction. My name is Ryan Vallance, and I'm the Vice President of the Kudoform Division inside Senko Advanced Components. So our division is working on fiber optic connectors that are using metallic components. The photograph that you see on this slide is an example of that. This one happens to be for silicon photonics. Happens to use our metallic optical bench component, which is a stamped metal part, and it connects 8 fibers to silicon photonic PIC. We're starting to explore how these products might be used in quantum photonic integrated circuits, but we recognize that these pose some really unique challenges. In particular, they're very likely going to be broader band applications. Wavelengths may range from UV through the vis to IR. And that means that they'll probably use heterogeneous platforms, perhaps dyes and substrates that have different coefficients of thermal expansion, which can be particularly a challenge if there's a broad range of operating temperatures. And this is particularly important when you stop and think about the very best single photon detectors still require cryogenic operating temperatures. So despite many of these packaging challenges, our goal is to deliver a fiber optic connector for multiple fibers with high coupling efficiency for these applications. Our current products are designed for vertical coupling using diffractive grating couplers. And these were originally designed for butt-coupled fibers that mount vertical to the surface of the QPIC. The grating couplers operate between the waveguide and between the core of the fiber, and they kind of serve two functions. There's mode field expansion, where we go from the mode field diameter in the waveguide and expand it up to the 10 micron, roughly 10 micron mode field diameter in the core of the fiber. And then they also cause the light beam to exit at a diffraction angle that's typically between 8 and 12 degrees. Now, our product takes a slightly different approach. We did not want to butt couple the fibers because of the reliability and size requirements for that. And so our connector routes the fibers parallel to the surface of the QPIC. And then we insert between the end of the fiber and the surface of the grating a reflective mirror. And that mirror can serve multiple optical functions. It can fold the light beam so that it enters at the diffraction angle of the grating. And it can also reshape the mode field diameter so that it's a better match to the grating. And because the fibers exit parallel to the surface of the PIC, we can achieve this in a connector height that's really a low profile. It's typically about 1 millimeter. We build these metallic PIC connectors from 2 components. The first one is a metallic frame that's usually made out of a low CTE material like Covar or Invar. It can be matched to the CTE of the substrate or the QPIC. And that frame has a window in it in which we insert a piece of aluminum that's commercially pure aluminum. This has the benefit of having a very high reflectivity across most of the optical band from UV all the way through IR. And then once that aluminum piece is on the inside of that frame, we stamp it with a hard tool and simultaneously form an array of grooves and an array of micromirrors into the aluminum surface. When that stamping process is completed, we have a component that we call a metallic optical bench. And that metallic optical bench is then assembled into our metallic PIC connector by placing the fibers into the grooves, dispensing an index matching epoxy, attaching a cover glass piece, and then curing the epoxy through the glass with UV light. So the mirror can serve as a lens. And so one alternative is to use that lens to simply re-image the core of the optical fiber. So in this cross-sectional diagram, you can see the light beam diverging out of the core of the fiber, shining onto our mirror, and then the mirror folds the light beam at the diffraction angle and then re-images the core of the fiber on the surface of the grating coupler. This is an advantage in cases where you have grating couplers that are already in the PDK, which have been developed and designed for butt-coupled fiber. In a sense, the mirror is serving to simply re-image the core of the fiber. The coupling efficiency in this arrangement can be as good as about 0.2 dB if the connector is perfectly aligned with the quantum PIC. The coupling efficiency can drop off pretty quickly due to the small mode field diameter, which, if it's about 9 microns, a simple offset parallel to the surface of 1 or 2 microns can cause that coupling efficiency to drop from 0.2 dB down to 1 or even 2 dB with a few microns of offset. So we're big proponents of using the mirror to form an expanded beam between the connector and the surface of the PIC. So in this case, you can have a mode field diameter that's about 35 microns or so, which is much more tolerant of misalignment between the connector and the QPIC. So right now we're offering a version of the metallic PIC connector with a mode field diameter of 34.4 microns. We think this is a good compromise. It offers a translation offset tolerance of plus or minus 3 microns. And can still maintain 0.25 to 0.5 dB coupling efficiencies. So it's really effective. And one thing that some people don't often mention when they talk about expanded mode field diameters and expanded beam is that it becomes more limiting. The tolerance on angular misalignment becomes more severe. And so we think 34 microns, 35 microns is a reasonable compromise between those two. I also wanted to share with you that Senko is participating in a very interesting quantum-related R&D program. It's called QPICs, which stands for Quantum Photonic Integrated Circuit Packaging. And we're working with Wave Photonics and Alter and a couple of universities at University of Bristol and University of Southampton. And the goal of this program is to really develop packaging templates that can be used to simplify and standardize quantum PIC packaging. So this first program is using our 8-fiber on 250 micron pitch metallic PIC connector. And vertical grating couplers that are being fabricated into Cornerstone's PICs. So I encourage you to stay tuned for this program. The final report is due next month. I also wanted to share with you that at ECOC a few weeks ago, we announced that we're really advancing the density of the fiber optic connectivity. We've now advanced beyond 8 fibers on 250 micron pitch and are offering 16 fibers on 127 micron pitch. And probably this spring we'll have 20 fibers on 127 micron pitch. We're expected to have that available by end of Q1 2024. So in conclusion, our metallic PIC connectors we think are a really interesting approach for quantum PICs. They use the reflective mirror as a lens between the fiber and the surface of the quantum PIC. And that allows us to not only fold the light beam so that we can have a low-profile connector, but also do some mode shaping or beam expansion. And if we do the beam expansion, it really relaxes the alignment tolerances, which can be a benefit for large operating temperature ranges or cases where you have CTE mismatch. And so I want you to continue to watch for the templates for packaging because those will allow you to get your quantum PICs packaged and assembled at Alter with their active alignment capability. So if this appeals to you and you want to talk about your particular application, please reach out to me at this email address or see me after the session. At this point, I'll stop for any questions.
Thank you, Ryan. Any questions?
Yeah, I can hear you. I'll repeat your question.
What kind of end-phase treatments are on those fibers to avoid back reflection, precision of the diversion point?
Yeah, so there's two options. For the most silicon photonics applications, we use an index matching epoxy between the end of the fiber. Yeah, so that prevents the back reflection. I think that for some of the quantum applications, particularly those that go down to cryogenic temperatures, we'll get rid of the epoxy. And so those would then have an 8-degree angle polish on the fibers. Okay. And then the optical path would be designed to accommodate that.
Great. Mm-hmm. Thanks.
All right, thank you very much. Any other questions? Nope. With that, I think, thank you very much, Ryan.
Thank you.
Thank you. All right.